Good morning, everyone. Welcome to Stantec's webinar on threat assessment for pipeline safety assurance. I'm Jerry Fraser. I'll be behind the scenes today, moderating this session. I'd like to welcome everyone on behalf of Stantec. Wanted to also let you know that our audience today will be on mute. We will be taking questions at the end of the presentation, but if you have questions during the presentation, please feel free to type them into the question box and we'll take those at the end of the presentation. To get us started, I'd like to hand us over to Dennis Zattery. Dennis, take us away.
Thanks, Jerry. Welcome, everyone. Thanks for sharing your time with us today. Just a little quick background on how we got here. Stantec Integrity Team has long been committed to advancing the industry through technical papers at events like NACE, IPC, PRCI studies. Clearly in 2020, the industry is going through an evolution in how that all looks. We thought this would be a great chance to network and connect with some of our peers on some of our experiences and philosophies and where we've come in threat assessment in recent times. And as of a note, Stantec is committed to presenting some technical papers at the upcoming International Pipeline Conference at the end of September, which is now a virtual version event. Advancing. Myself, Dennis Zattery, the Vice President of our Asset Integrity Services team at Stantec, been with the organization for almost 20 years in a variety of integrity roles. James?
Good morning, it's my pleasure to join you today. My name is James Ferguson. I have been with Stantec for over 15 years, and my work in integrity started in internal corrosion and then went into inland inspection assessment, pipeline design, integrity management programs, risk and safety management systems. Graham, would you like to introduce yourself?
Good morning, everyone. My name is Graham Adams. I'm one of the senior integrity engineers here at Stantec. I've been with the team for a little over 10 years now, and most of what I do is engineering assessments and threat assessments on pipelines. I've completed about 250 of these, primarily regulatory assessments, across Canada and the United States. So that is most of what I do and a lot of what I'll be talking about today.
Just a note to the audience, all three presenters will be turning our webcams off to focus on the presentation content. Just an outline of how this presentation is going to work. We do expect the formal content to last about 45 minutes. We are leaving a Q&A question at the end. We had a few comments already by registrants, so thank you very much. We'll try to address that during our conversation and discussion. And it'll be a combination of myself with the introduction, James Ferguson, followed by Graham, and then finishing with James. So in terms of our safety moment, we're actually making it a safety/market moment. I wanted to highlight a success story in the pipeline industry. For those in Western Canada, you might be familiar with a pipeline called the APPL, the Alberta Products Pipeline. It was built in the 70s as a vital infrastructure link, shipping refined products between central Alberta. It's about 320 kilometers long, and like I said, it was built in the 70s. What you're about to see is an excerpt from a presentation that was given at IPC 2012. This project underwent a massive risk assessment and life cycle study. Every one of those dots on the screen represents a joint of pipe on the 300-kilometer pipeline. This is just an example of the type of risk assessment data that was compiled on this level of pipeline. And I just demonstrate what happens over time with individual joints of pipe moving through a risk assessment philosophy and approach. Clearly, more and more of the joints of pipe without mitigation move into the red hazardous area. So the reason this is a relevant story is this went to management planning, so it went through a life cycle study, including cost benefit analysis. And as of 2012, they decided within a 10-year window, the pipeline would probably exceed its appropriate lifetime. So what's exciting is that in 2020, the new version of this pipeline has been installed and commissioned. This pipeline with all the dots on this matrix has been replaced and decommissioned. Vital infrastructure link was operated for 40 to 50 years in a safe, reliable mode, understanding that there was a point in time when it would no longer be economical and viable to continue operating that pipe. So just an example that, we hear the negative parts of the pipeline industry all the time, but this is an example of excellent life cycle management approaches. On that note, I'm going to turn the presentation over to James Ferguson. James, are you unmuted?
We're just trying to unmute James. Bear with us a second. Go ahead, James.
Thank you very much. We're here now. Technology is what it is. The example Dennis shared shows safety management in action and the efficiencies gained from having advance notice of increasing maintenance and repair costs. In this case, permitting the operator sufficient lead time to engineer and install a replacement for the pipeline. In the broader perspective, a full review of safety may be necessary at various points in a pipeline's operating life cycle. This could include reactivating an idled line for product shipment, increasing the maximum allowable pressure on the line for throughput, or simply a routine audit. There is a consensus in industry that achieving outcomes like the one that Dennis talked about in our market minute, those successful outcomes depend on some basic steps. We need to identify the problem, and clearly we need to break that problem down in terms of threat assessment. In the last stage, we also need to evaluate the impact of uncertainty of that threat, and that is the risk assessment stage. We will use the flow chart on the right of the screen to guide our discussion today. The purpose of our panel today is to show that threat assessment can result in efficiencies throughout the full operating life cycle of an asset. First and foremost, the job of safety assurance is to close the gap on risk of loss containment. We need to uncover threats that could exceed the risk tolerance. In the next element, it would be beneficial for efficiency reasons and to benefit our overall enterprise, if we could increase the lead time for maintenance and inspection, for identifying maintenance and inspection activities. We could gain substantial efficiencies in field execution for work planned and defined a year or more in advance. In addition, it would be very beneficial and a clear indication of an efficiency if preventative maintenance programs for lower risk threats could be scaled back. How could we do this? Well, certainly we need to do this with safety in mind. And the way that we would strive to do this is to achieve certainty about the level of risk that the threat poses and base any reductions on keeping that level of risk within the safety tolerance. And in the final and last objective that we're going to strive for in our discussion today is we'd like to leave the operation with excellence in asset management. We'd like to create the basis and the means to lower the cost of operation in terms of dollars per throughput, and also gain flexibility to align out of service maintenance with shipper schedules. Let's start with looking at the threat identification step and how we can go about doing this to meet our objectives, keeping in mind, as API 1173 suggests, what can go wrong is the purpose of doing this assessment. The approach that we found works best relies on analysis of the fault tree of possible causes of loss containment. Drawing on an assembled team representing design, installation, operations, maintenance, integrity, and safety management, the purpose of this is to stimulate the imagination of our participants to identify potential hazards or threats and the causes of those threats. Structure and direction are provided for the participants with standardized guide word prompts as each element of the fault tree is reviewed. That all sounds good. Let's see what this looks like in action. Again, the purpose is to broadly review all credible threats acting on the pipeline and to identify controls that are already in place to prevent and mitigate each threat. If we look at the 9 categories of threats that are commonly used in industry, in this method, a breakdown of more than 100 causes is reviewed. For example, in the area of environmental and process cracking, we're interested in the causes of those things. On the SCC side, if we're looking at SCC, we're interested in despondent or non-functional coatings. What is the condition of the coating? What type of material do we have for susceptibility? Is the environment conducive to near neutral or high pH? And do we have sufficient stress and cycling on the line? For process cracking on the inside of the pipe, we were going to focus mostly on the types of cracking that are prevalent for pipelines, midstream pipelines. In a liquid world, that could include hydrogen-induced cracking, sulfide stress corrosion cracking, and there's a few more mechanisms that are less common. Switching tracks, again, for illustrative purposes, let's examine what would a breakdown, what would this fault tree say about the external interference threat, termed third-party threat in the US. We're definitely interested in things like, do we have clearance when we have crossing utilities? Is there any chance of undermining under the pipe? And then what all possible ways can external interference or third-party incidents occur? Broken down by the type of personnel who are doing work in the vicinity, including third-party, unrelated personnel. And we're looking at all those elements, including depth of cover, loss of cover, how is this right-of-way being used in terms of agriculture, if there is any, so on and so forth. And we furthermore have to understand and examine what is the possible impact of pre-existing deformations. Is there the chance that we have a growth mechanism for those, including dent fatigue? Okay, so what does this look like in action? We've talked about the concept, we've talked about the details. Here's an example that we can consider. And I just want to mention that whenever we do this method, there's almost always a surprise that turns up. In this case, our study group was looking at a 42-inch river crossing on the North Saskatchewan River in Edmonton. The crossing was installed using the open trench method. And the group was asked the question, how do we know that we don't have a threat or a hazard from the backfill process? And as the group considered this question, it turned out that the backfill, the post-construction inspection for the backfill had not occurred. And when they did that, a number of years later, they found that they had a challenge with that backfill, and that they had a remediation in terms of river bottom scour to take care of. At this time, I'd like to turn it over to Graham. I'd like to turn the mic over to Graham, who will possibly remember to turn on his mic, unlike my error, and would provide us a perspective on the next element in safety assurance.
Okay, thank you, James. So as James mentioned, I'm going to be talking now about how we're going to conduct the threat assessment and move on to the next step of this process. So if we go back to our flow chart, this is where we are in the process right now. We've done our initial hazard and threat identification, as James mentioned in his section, and we're now going to gather some data on the condition of the pipeline, looking for what hazards are active on the pipeline and what information we have present in terms of dealing with those mechanisms. So if we have information sufficient to address each threat, then we're going to go into the next step of the process, which is an engineering critical assessment. That's terminology that's going to be familiar to those of you who are from the United States. For the Canadians, you're probably more familiar with the phrase fitness for service assessment. And then from there, or going straight to there if we don't have sufficient information yet, we're going to move into the risk assessment portion, which James will talk about at the end of the presentation. This is probably one of the most comprehensive and expansive types of integrity assessment that we can do. And as a result, this is something that I feel confident I could speak on at a week-long course. And unfortunately, I only have about half an hour to work with today. So there are three main elements that I want to discuss today. Review of construction records and MTRs, the inspection, QA, QC review process, and how we actually go about assessing the results of an inspection once that's been put through the review process. So as I mentioned, this is a very, very broad and expansive topic, and as a result, it's not typically a one-person job. When I'm conducting a threat assessment, at absolute bare minimum, I'm talking to at least half a dozen other people, and more frequently, that number is between 10 and 20. And that'll range from everybody from other members of the Stantec team, our ILI specialists, our internal corrosion specialists, our geotechnical and geohazards team. That can consist of inspection vendors and their representatives, and that can consist of staff on the owner-operator side of things, whether that's field staff or integrity staff responsible for overseeing the asset in question. What's nice is that because we have all these different eyes on the pipeline and all these different expertise that are threading into this assessment, when we do a comprehensive threat assessment, it really is an excellent opportunity, not just for a good, thorough evaluation of the pipeline's fitness for service and its integrity practices, but also an assessment of the integrity management systems that are supporting that asset. So we can then ask ourselves, are those systems doing their job, or is there some room for improvement? So the overall goal of a threat assessment, what we're trying to answer is the pipeline fit for service today under its present operating conditions? If there's any proposed changes, is it fit for service under the new operating conditions? And finally, taking a look into the future, both short and long term, what activities will need to be carried out and under what timeframes in order to continue safely operating the asset and maintaining its integrity. So we're going to start by talking about construction records and MTRs. And when I first started doing these assessments about 10 years ago now, this was an element that I probably did not pay enough attention to, because at the time I figured if we've got up-to-date inspection data, then what do we care what the pipeline looked like when it was put in the ground, which may be more than 50 years ago. I've had a significant change of heart in the years since then, mostly borne out by experience. Because those initial construction records give us our best view of the pipeline at the time that it was installed, and sometimes beforehand, at the time when it only existed on sheets of paper. So these records can give us some understanding of what the design philosophy was of the pipeline and under what regulatory structure it was built to, what was the code that was used for the design of the pipeline. So I've put a phrase on there, traceable, verifiable, and complete, which comes from PHMSA regulations, so it will be very familiar to the Americans in the audience. And that's a key guideline for any records that are going into a threat assessment, is we want them to meet that standard of being traceable, verifiable, and complete. And construction records are some of the best way to do that. This is source documents. You really don't get any closer to the heart of the pipeline than this unless you're actually digging it up and looking at it in the field. So what sorts of records are we looking at? I've got a list up there on screen: hydrotest documents, weld inspection records, MTRs, as-built, and in particular, the license submission packages that are sent to the regulators when the pipeline is first constructed. Those are absolute treasure troves of data if we can get a hold of them. So those are always things that I like to have if at all possible. So just as a heads up, there is an interactive portion of this presentation. So I just want to make everybody aware that as we get a little bit into this slide, there's going to be a poll that pops up on your screen. So one of the downsides to construction and MTR records that is worth mentioning is that these are records, out of all the records on the pipeline, these are the ones that are most frequently either incomplete or missing altogether. And that's especially true if we're talking about a pipeline that's either older or has changed hands at some point during its lifetime. This is an area where I find that the industry has had a weak spot. It's getting better, particularly over the last few years. There have been some legislative changes that have closed some loopholes that implicitly encourage the records not to follow a pipeline from one owner to another. But unfortunately, those changes by their design are not retroactive. So even to this day, if I'm given a pipeline to assess and I notice that it's either more than about 30 years old or it's changed hands at some time more than 10 years ago, I can usually guess that I'm not going to get very much in terms of construction records, and I'm usually right in that assumption. So for that, we need to consider how we're going to compensate for those missing records, and that will depend on what the record in question is trying to cover, whether we're talking about more up-to-date inspections, some destructive testing, or something of that nature. So I'm going to ask Jerry to pull up the poll question now, or Jennifer. And this is the interactive portion. So the question for those of you in the audience, and obviously this will apply to the owner operators, is what percentage of your pipelines do you believe that you have records, construction records that meet that PHMSA standard of complete, traceable, and verifiable? So I'll give everyone a little bit of time to answer that. The reason why these are important is because I find that most owner operators today use some form of pipeline inventory system as a one-stop shop for their pipeline data. So that's frequently a pod style database, or it can be an Excel spreadsheet. But quite typically, that's where people go for their information when they need to do an assessment on the pipeline. The downside of that is that we need good data to feed into that database in order for it to be viable, and sometimes that good data isn't available. So a piece of data might be based on an assumption or based on an inference from some other record, and the fact that that data is assumed doesn't always carry over into the pod's database and isn't always apparent to whatever engineer or integrity staff is looking at it. Okay, so I'm hoping that people have had enough time to look at the question and answer it now. So if we could just put the answers up on the screen. Oh, there we go. Okay, so that's actually about what I was expecting to see. So that sort of 25 to 50% range is the pipelines that have good solid data. And then some of you guys are getting up into the 75 and 100% range, which is great. But this is good feedback, and this should just show that this problem, this issue of missing construction records is not an uncommon one, and it's one that we see in the consulting world and have to work with quite frequently. Okay, if we can go back to the presentation, perfect. I'm going to take control again here. Oh. Okay, there we go. That's our poll question. So this is an example that I've got at the bottom of a pipeline where we ran into this exact issue and the perils of working off of one of these pods databases without tracing the records back to their source data. A fellow engineer and I were asked to assess a pipeline. This was about 5 years ago now. We were given the extract from the pods database, and it said that this pipeline was constructed in 1989. So not a terribly old pipeline. But as we started assessing this pipeline, we started having reason to doubt that that date was accurate. We looked at some excavation data, and this pipeline appeared to be coated with polyethylene tape, which this particular owner operator did not use on pipelines that late. Most of their 80s vintage pipelines were coated with extruded polyethylene. So we had to go dumpster diving for these records, and it wound up being quite an ordeal. This particular pipeline had been through several license changes in its lifetime, and even went through one period where, due to a licensing error, it was not properly licensed for a period of about 10 years. So when we finally sorted back through all the history and got to the original construction records of the pipeline via the regulator, what we discovered was that this pipeline had actually been constructed in 1962. So it was about 30 years older than we assumed. And this had fairly profound impacts on our assessment of the pipeline, particularly in the realms of fatigue, where all of a sudden this was now designed to a different design philosophy and construction code. So it was believed to have low frequency ERW welds instead of the high frequency welds that had been assumed. And it also had some impacts on our corrosion growth assessment. So one piece of data that was based on one slightly incorrect assumption had a fairly significant impact on the integrity outlook of this pipeline, which is why we want these original source records wherever we can get them. So let's move on and talk about inspections now and the QA/QC review process that goes into them. Inspections tend to be the meat and potatoes of a comprehensive threat assessment. These are our most up-to-date records on the condition of the pipeline and what flaws and features exist on the pipeline as of the date of the inspection. Over the last few decades, inline inspection has obviously become the industry standard. The most common type of tool that we typically see is MFL caliper IMU. That is by far the most common tool that's run in the industry to date, and we're looking at those pretty much on a daily basis at Stantec. There are some other, not quite that common, but still fairly common tools in the form of things like ultrasonic wall measurement, CMFL tools, and then slightly less common again are some of the UTCD and EMAT tools. And then you get into the more esoteric tools that tend to be run to address specific observed needs and are not something that we would typically see run on an entire system. So these are things like strength measurement tools, where the tool is running through the line and reporting back on the yield strength and the UTS of the pipeline, or something like an axial bending strain tool. So each of these tools operates with a different physical mechanism and requires a different QA/QC procedure. So we wind up having to look at a lot of different types of ILI data and understand how we need to assure that that data is accurate and telling us what we need to know for our assessment of the pipeline. Now, I'm going to be talking a lot about ILIs in this presentation because it is the most common form of inspection that's used today, but it's not the only kind. There are other pipelines out there that are non-loggable for one reason or another, and those pipelines still need inspection as well. So there's other technologies out there. I've got a few of them listed on screen here: direct assessment, crawler tools, guided wave, acoustic tools, camera tools. And everything that I'm about to say in the rest of this presentation is just as applicable to those. We do at Stantec occasionally have to do a threat assessment on a non-loggable pipeline, and I've got an example of one here. There was a pipeline based out of Saskatchewan that we were asked to assess. It was a relatively new pipeline. It was a little under 20 years old when we were asked to assess it, but it had not been inspected. It was a non-loggable pipeline, and the owner-operator was doing a engineering assessment that was mandated by code because there was going to be a significant pressure increase that was impacting this pipeline. And so the question for us was, can we do an actual engineering assessment without inline inspection data? And what needs to be done to facilitate that? So the answer to the first question was yes, absolutely. And the second question, we went through this entire process that we're describing in this presentation today, starting with the threat identification. We took a look at the data that was available for this pipeline in order to do a threat identification and risk assessment to determine the most significant threat facing the pipeline, and that turned out to be external corrosion. So as a result of that, the decision was made to run an ECDA on this line and combine that with some analysis of the cathodic protection data in order to form an understanding of what the external corrosion was doing on this pipeline. And from there, that wound up being the basis for a more comprehensive threat assessment, with most of the other threats being dealt with on the basis of risk assessment, which again, we'll talk about later in the presentation. So the picture at the bottom here is a good example of why we have the QA/QC process for our inspections. This comes from a 2012 inspection. This is a gouge on the pipeline. It looks like somebody used a backhoe and happened to hit the pipeline. We don't know the circumstances that originally caused this gouge, but this pipeline was originally inspected with an MFL and caliper tool, and the tools of that vintage were not particularly good at identifying gouges. So our QA/QC process on the ILI that was run on this pipeline identified this as a dent with metal loss that had a very, very unusual profile. And it didn't look just like a dent that was coincident with corrosion, which was what it was reported as. And so we wound up flagging it, recommending it for inspection, and then it turned out to be a gouge, and that was a code mandated repair. So this particular joint of pipe eventually got cut out and replaced. What's on screen right now is an example of the QA process that goes into an ILI. So don't strain your eyes trying to read what's on the screen. This is mostly here just as a visual for what goes into the QA/QC process. This is our QA/QC checklist for an MFL tool, and it's actually the shortest checklist that our ILI team uses. As mentioned earlier, MFL tools are very common. There's lots of industry knowledge behind them. So the QA/QC process behind them is comparatively simple compared to something like UTCD. The UTCD checklist is about 3 times this long. I don't think I could fit it onto a single slide without making it about 2-point font. So just some examples of the things we look at in our QA/QC process. We look at the physical parameters of the inspection run. Was the tool within its velocity constraints the entire run? Were the magnetization levels proper? Were there any critical anomalies that were reported that would require immediate attention or an emergency dig? Are there any signs that there was degraded or missing data? Were all the sensors reporting properly? And then we actually sit down with the ILI vendors and we wind up doing some spot checking. So we'll go through and we'll spot check a few points on the pipeline and say, okay, did the final report reflect accurately what was seen in the raw data, or does there need to be some form of revision made to make sure that the data is accurate? And here's a good example of, again, what the QA/QC process can yield. This was a pipeline that we were asked to assess in 2012. It had been inspected with an MFL tool in 2010. This was a small diameter line. It was low pressure, so there wasn't much concern about metal loss rupture. It was mostly leaks that were the concern. The ILI data, when we initially looked at it, looked fairly benign. Almost all the features were less than 30% deep, with a mix of internal and external corrosion. So not something that looked particularly exciting on first glance. But as we did the QA process and we compared it to some of the excavations, what we found is some tremendous undersizing. So we had some features that you can see at the bottom here that were, oh, sorry. Did an accidental click there. We had some features at the bottom here which were undersized by almost 40%. The ILI tool called them at about 13-14% deep, and they were found in the field to actually be 53% deep. So what we determined through our investigation is that this line was suffering from MIC, microbially induced corrosion. It was creating pinholes on the pipeline, which are corrosion flaws that have a very small cross-sectional area. And that was a type of corrosion morphology that this particular form of inspection tool was not able to accurately detect or size. And so the end result was some fairly dramatic undersizing. The owner operator in this case did request a regrade of the ILI data, but even after they did so, we had very little confidence that that data was actually accurately reporting the state of the pipeline. And so we in essence had to discard that data and do a completely different assessment on this pipeline based on internal corrosion risk factors. We wound up doing a complete overhaul of the internal corrosion mitigation program, increasing the pigging frequency, introducing a biocide into the system, and installing real-time monitoring sleeves. And this wound up being a success story. We were called back a few years later to look at the same pipeline, and we determined that the internal corrosion growth rates in areas where corrosion growth had previously been observed to be occurring had dropped to pretty much nothing. Okay, so we've now done the QA/QC process and we're now into actually assessing the threats. So how do we go about doing that? Well, There's a lot of different types of threats out there. James gave that table at the start of the presentation with the 9 categories of threats and 100 different subcategories. And a lot of those categories, and even within those categories, some of the subcategories have different assessment methodologies associated with them. On top of that, depending on what tool reported the feature in question, that's also going to impact how we assess the features. Our assessment has to include things like tool error. Where was this feature located on the pipeline? Is it close to a girth weld that's going to introduce more error? What's the morphology? Is it like those pinholes where there's concerns that the tool didn't size it properly? What type of feature is it? Some inspection tools or some inspection technologies are not capable of picking up certain types of features. What's the location factor in that area? What's the corrosion allowance? Are those things there that are going to impact the acceptability criteria? How fast is the feature growing if it's corrosion damage or if it's fatigue cracking? And then one thing that I want to call out in particular is, are these features interacting with a different type of feature? And I want to call this out and give it its own section, because when we're talking about a comprehensive threat assessment of the pipeline, that's one of your best opportunities to catch and identify and assess these interacting features. Unlike some of the more routine inspections where, if we're, for instance, trying to analyze the output of one ILI, and we're looking primarily at that ILI and maybe some of the historical ILIs as well, when we're talking about a threat assessment, we're trying to put all of the integrity data of the pipeline on the table and understand how those various different threats are interacting. No one technology can assess all types or can inspect and detect all types of features. And so if we're using multiple different technologies and multiple different inspection methods and analyses of the pipeline, it gives us a better chance to catch and identify these features. So in terms of how we're assessing the output of these inspections, there's a variety of different methods available. I've got some of them on screen here. This is not a comprehensive list, and again, I'm not going to go through everything on the screen here, but this gives you an idea of some of the assessments that we do as part of our analysis of an inspection tool. There's lots of different types depending on whether the feature is not interacting with anything, which is the first column there, or is interacting with the secondary feature, which is some of the remaining columns. And as mentioned, this is not comprehensive, so there are other types of inspection methodologies that we can wind up using as well. So how exactly do we overlay these data, and what's the output as a result? This is an example of one type of data overlay that we can do, which is spatial data integration, where we're using common spatial points like AGMs on ILIs to tie various data together and use that to identify interacting threats. So some examples of this, we can interact metal loss ILI data with cathodic protection data in order to identify places where external interference might be happening or where low CP levels are fueling external corrosion growth. We can correlate caliper data to geohazard data or bending strain data to geohazard data in order to identify areas where a pipeline is experiencing stress from an unstable geohazard. We can correlate caliper data to aerial patrols in order to identify possible locations of third-party interference, where additional protective measures might need to occur to prevent future instances of damage. So what you're seeing on screen right now is another one of our tools that we use for data integration. This is our ILI interacting feature identification tool. So this is a database that can take ILI data from any different ILI vendor, multiple vendors, multiple different technologies, and it overlays them together. It correlates them to ensure that we're looking at the same joints of pipe in each data, and it will axially and circumferentially attempt to overlap various features and identify which features might be interacting. And where this is particularly useful is if you have multiple different technologies that are designed to pick up different types of flaws. So for instance, if you're comparing a UTCD tool, which can be used to pick up crack-like features or cracking features, and you're comparing that to something like an MFL tool, which can pick up metal loss, or a caliper tool, which can pick up dents. So this will give you some interactions that some of the other, that you wouldn't necessarily pick up just by looking at one type of tool in particular. So let's take a step back now and have a look at what the entire process looks like. This is an example from a project that we did a couple of years ago where we were assessing a pipeline that had a significant number of geohazards on it, and there was concern that some of these geohazards were posing a significant threat to pipeline integrity. So what we had is first we looked at the geohazard data in isolation, as well as the ILI data in isolation. This pipeline had some IMU data associated with it that we were able to do a bending strain study with. And then once we had those two separate data analyses, we actually overlapped them on top of one another using spatial integration. And that was able to give us an idea of which of these geohazard areas were actually seeing the most damage according to what the ILI was turning up. So that gave us a prioritization of which geohazards required further analysis in the form of finite element analysis for strain. Based on that analysis, we were able to estimate the remaining life of each geohazard, and that allowed us to generate a schedule and a prioritization for monitoring, mitigation, and repairs in the various geohazard areas. Oh, there we go. Sorry, lost my mouse for a second there. So this is a visual representation of, this actually wasn't the same project, but it was a very, very similar one using similar analysis. We had multiple ILIs run on this particular pipeline, which included an IMU tool, which was reporting bending strain, and an axial strain tool. And in addition, we had geohazard data on this pipeline. This particular geohazard area was noted by geotechnical assessment to have quite a high probability of incident. And so there was a need for us to go in and take a look and do a more comprehensive evaluation of what this particular area looked like. So what you're seeing on screen here is an overlay of the ILI data, which are the various little pins that you can see put on there from Google Earth. So we have some axial strain features and some strain features, as well as the findings from the geohazard study. So the purple band that you see here is an area where the pipeline is actually in tension. The red area is where the pipeline is in compression. So you can see quite visibly that this pipeline, this particular slope is eroding. It's starting to slide down into the valley here. And it's having some actual physical effects on the pipeline. So combining all this data, we were actually able to get a very comprehensive view of the pipeline and actually put some quantitative numbers to what we were seeing and use that to plan our recommendations for future mitigation activity. All right, and with that, I'm going to turn things back over to James, and he will talk about the last portion of this process.
Thank you, Graham. Yeah, and definitely an excellent example that you just showed us of a pipeline threat related to a slope that can be studied using numerous ILIs, based on which interacting features can be visually understood through GIS. This is all very clear and very well done and very amazing. The point at this point, we need to pause and just consider that it may not be enough to have a GIS analysis like this, a deep analytical analysis, and the condition assessment behind it for each of those individual features to justify a multi-million-dollar slope remediation project. We probably will need, so in addition to those advanced analytics, we probably will need to know that that decision is going to, for construction, is going to hinge on a further analysis, and that analysis is the estimation of risk and the impact of uncertainty. Risk is a means to quantify the likelihood and impact of an event that has not yet occurred, but can be anticipated based on information that is known. The known information, in the general case, the known information for risk assessment includes the individual threats identified among the 9 categories of threats. It also includes the assessment of consequences grouped primarily into the external categories shown, as well as consideration for the direct financial impact to the company, impact due to loss containment. The types of external impacts that we want to consider have expanded recently. In 2019, the Canadian Pipeline Code, CSA Z662, added designated geographical areas, or DGAs. On the US side, included in Part 1 of the Gas Mega Rule, lawmakers expanded the definition of covered segments to include moderate consequence areas, MCAs. Many pipelines are logistical links in bringing energy to consumers and businesses. And as such, potential disruption to these essential services is yet another type of external impact. Switching back to likelihood, no matter what type of knowledge we have gained as a result of our threat identification and condition assessment, we should be able to do a probability assessment. In the first case here that we're looking at, without any condition information and only a minimum of information about the pipeline, a historical probability of failure can be estimated based on published pipeline incident statistics and correlated based on similar service and materials. In the next case, we're looking at a qualitative threat assessment incorporating the judgment of subject matter experts is a valued form of probability assessment. The SME criteria, we have found that the SME criteria can be encoded and more finely correlated to historical performance to quantify the more accurate probability of failure. We will look at an example of this in a minute or two. Looking at the case where we have some condition information, however, we may not have a completely successful inline inspection, or that ILI may not be capable of detecting the features which are of interest. They may be too small, they may be below the detection threshold. We can bring a distribution analysis into the study, and we can use that to extrapolate on the feature distribution that we do have. We will look at an example of this one as well. And then in the most common case, we do have an ILI, it did work, it passed all of Graham's checks, and the effort now is focused on estimating the effective uncertainty in feature sizing that ILI inherently has. And the probability of failure is then based on the overlap between the load and resistance curves for each feature. Ultimately, these different types of probability assessments have the power not only to reduce the risk of loss containment, but also to reduce the cost of the IM program itself. Here are two examples to illustrate this. In this slide, we see that, as I mentioned a minute ago, it's not uncommon to have difficulties executing inspections in the field. In this example, where a long seam inspection could not be completed, a statistical distribution analysis was used to examine the probability of exceedance for the portion of the pipeline that was not inspected. In this case, we are looking at a pipeline that is low on the pressure scale, below 20% SMICE. Based on that low pressure, we know that the failure mode would be a leak and not a rupture. And for that, that allowed us to concentrate on the depth data for this analysis. To err on the side of safety, all of the seam anomalies that were found through the inspection and were considered in this analysis, whether or not they were active or stable. And in the end, the analysis found that the probability of having a feature greater than 30% wall thickness in the long seam is actually less than 10 to the -5. And that, of course, puts this particular threat well within the risk tolerance of the operator, and the remaining inspection did not need to be completed. In this second and final example that we want to share, The judgment of our Stantec geohazards subject matter experts, they looked at this right away for the pipeline at the design stage, and they examined it for susceptibility to types of slope movement that are prevalent in the area. This review included looking at the potential for rotational and compound landslides, spread, so-called Cheecham type landslides, fairly unique, gullying, and increased instability in the event there was a wildfire. Based on the combined POF of all of those characteristics, the risk of loss containment was found to be, again, within the risk tolerance of this particular operator and at this location. And as such, at the design stage, no additional mitigation was needed for this slope. The due diligence was done, the checks were done, and the standard construction practices were sufficient in this case. At this point in time, I just want to say, as attendees for this presentation, for this panel, you've invested part of your day in listening to Stantec's methods and approaches for pipeline threat assessment. And we would very much like you to let us know, how did we do? Did we communicate and did we demonstrate the benefits that we set out to? For example, it is the professional duty of an integrity responsible person to close the gap on the risk of lost containment. In our discussion today, we covered reliance on traceable, verifiable, and complete records. We talked about comprehensive threat identification, ILI quality assurance, interacting feature analysis, and the impact of uncertainty on risk assessment. We furthermore discussed the increased, that we're striving to provide increased lead time for inspection and maintenance. This is enabled using the types of growth analysis that Graham touched on for time-dependent threats, corrosion, deformation, and cracking. It's also, we can also make strides in this area through investigation of subcritical features, understanding features that may not be repairable in the present context, but through examination of them will give us an edge in terms of understanding them and predicting the future as far as those features may grow. We're definitely striving to scale back on any programs under the current economic climate. We definitely want to demonstrate any programs that can be safely reduced. And the way that we are going to do that, and the way that we talked about doing that, is simply by dialing in through enhanced data analysis on the ILI and DIG program. We're also very concerned and concentrated on mitigating threats at the design stage and the prevention aspect, reducing the life cycle mitigation cost. At the end of the day, if we have helped in demonstrating how to achieve excellence in asset management, you can take that to the bank. Once you have your long-term inspection and maintenance plans developed, communication of those plans with stakeholders allows them to work around those efficiently as part of the broader organization. And there's also the opportunity to look at the present value cost comparison at the end of an asset life cycle and determine the appropriate time and plan well in the future any replacement that's needed. That concludes our topic, and back to you, Dennis, as our moderator.
Thank you very much, James and Graham. Appreciate that we are getting closer to the end of the hour. We are going to field some questions and answers that came before and during. So thank you very much. And for those that have to sign off at the hour, we appreciate that you've shared this time with us already. I'll start off by one question that was asked before the presentation even occurred. One of the registrants had a question. How relevant is this methodology and process for non-oil and gas pipelines, including non-metallics? I'll speak to that. For those that aren't familiar, Stantec is a very broad consulting organization, and we do have a very advanced water management team. They also have a very advanced specialized team in condition assessment of water and sewer pipelines. In fact, Stantec has partnered with the Water Research Foundation to do some studies on condition assessment. There is a lot of advancement in technology of inspection tools, eddy current, UT, non-intrusive inspection of water pipelines. And secondly, to go with that, is the methodologies and the structural assessment of water pipelines that do have damage in them is advancing very dramatically in the last 10 years. And that includes a combination of concrete pipes, non-metallics, cast iron, ductile iron. So I can speak to the fact that if anybody's curious, we do have talent and skills in the area of non-oil and gas pipelines, similar to what James and Graham just talked about. Graham, we had an audience member ask a question about your case study specific to MIC and internal corrosion. The question came up, how did they actually repair or mitigate the deep pits in the pipe? Because once corrosion, hits a 50% threshold on a pipe, Graham, it's hard to actually stop the corrosion in it. So how did that get adjusted in the program?
Yes, excellent question. So this is going back in the memory banks a little bit, but in this particular case, most of the deepest features where internal corrosion was occurring were actually removed. So they were cut out and excavated. So for instance, the two 53% deep features that were visible on that slide were all cut out. Most of the ones that were left that were made the subject of some of the real-time monitoring were more shallow features. Those were treated by cleaning pigs. So I believe from this is stretching back a little ways. This project was about 8 years ago now, but I believe the real-time sleeves were installed on areas where the corrosion had not yet gotten to a point where there was significant concern that the MIC had formed a cell that was not going to get hit by the biocide. So the introduction of the biocide combined with the scraper pigs going through the pipeline to clean away the biofilm appeared to do the trick, because we were not able to detect any corrosion growth when we went back to the line a few years later.
Thanks for that follow-up, Graham. I think it's very clear they had to cut out the deepest pits. As we all know, you can't mitigate those once they hit a certain depth. James, a question about data integration. Can you share what types of public data are available that we use for spatial data integration?
Absolutely. Of course, just to start with, on the US side, there are clearly available public data sources related to the population density and other impact receptors for possible pipeline spills. On the Canadian side, it's much less organized. We need to go to numerous different authorities. We need to go to Statistics Canada for population. We need to go to the regional authorities for data on water. And in some cases, those data sources are considered to be confidential for obvious reasons, to protect those data sources from potential adverse actors. They're really concerned actually about the threat of terrorism. So with all the right confidentiality and agreements in place and a lot of legwork, Stantec's geomatics team goes through and comprehensively gathers up all the data from again, numerous different sources. I would estimate that the simple screenshot that we showed there on the slide, that relied on approximately 15 different data sources from different government agencies.
Thanks, James. Another question related to the case study, but I'll direct this towards James. It's a question about when you can't inspect for crack assessment. So if you're doing a non-loggable fitness for service of a pipeline for cracks and there is no ILI inspection data, meaning no population of known cracks on the pipe, James, you would normally use a just surviving flaw assessment technique. Any thoughts and comments on how you would quantify the number of digs and the number of features needed to be statistically accurate on doing that assessment without an ILI run?
Yeah, that's an excellent question. The question relates to probably one of the most threatening flaws, and also the type of flaw that is the most difficult to assess, even when you have an ILI data set. So the process would be to look at the susceptibility first. The susceptibility in terms of pressure, pressure cycles, and the materials, the vintage of materials is a big one. So to truly understand the susceptibility and correlate that with the the known information from industry about the pipeline, typical pipeline performance for that vintage and for that construction, is going to tell us a lot about whether this is a threat that we probably just need to figure out how to ILI, how to run the ILI, or whether this is a threat that we can then now pursue an SCCDA approach. So the number of digs is relevant to the SCCDA method itself. It's subject to the nature of the pipeline. It's subject to all of the variables that we have. Stantec has done work in this area, extensive work in this area in the past, and we published at least 2 papers in industry in IPC on a statistical method for approaching SCCDA. Which could be extrapolated and applied to long seam as well. A very complex topic and a lot of knowledge and expertise goes into studies like this. So thank you for the opportunity to discuss that.
Thanks, James. It is past the hour, but I'll continue to take a few questions. So Graham, specific to you and your ILI technology suite, dealing with selective seam corrosion, do you find that given that any ILI is going to have an issue in finding or specifically sizing seam corrosion?
Selective seam corrosion, that's an excellent question. My initial reaction to that would probably be CMFL tools would be the tool that I would expect to have the greatest success in detecting that. We do find we have a lot of clients who are dealing particularly with pipelines that were installed before 1970, issues with seam weld integrity, including selective seam corrosion, and CMFL has generally been the most successful of the technologies that we've seen in identifying and quantifying that threat.
One of the things that I can add to what Graham just shared is that CMFL tools have their work cut out for them. It's an extremely challenging type of physics, and the features and the metal loss that is expected with selective seam weld corrosion may be very small in relationship to the magnetic flux pattern itself. So in our experience at Stantec, working with Graham and others, we have found that the CMFL tools are great at identifying things and sizing things on a relative basis. Frequently, the sizing that comes off a CMFL tool for a long seam feature or a selective seam feature may be quite a bit less than the actual depth that you find in the field. And that can lead to a lot of uncertainty around the veracity of the tool and the validity of the tool. We've found that even though that is the case, that the CMFL tends to undersize, it does rely on some very fundamental, some very fundamental magnetic flux principles, and it is worth pursuing the most concerning features from that CMFL tool, and essentially using that as a guide for an DA, a direct assessment approach.
I'll go back to a question that was offered to us before the session started, and I'll direct it to James. What role will advanced technology, and I think when we think about technology, James, we could think both inspection, so hardware technology, and probably data technology play in doing threat assessments in the future. So how will technology change our future?
Well, it's a great perspective. I think technology has already changed our future. Obviously, we do have more advanced tools. Certain tool vendors are coming out with better and better and more accurate physics and sensors and analysis for the cracking threats, the most challenging ones. Today we talked about a couple of tremendous examples that, I feel like they're really tremendous and leading examples of how Stantec can bring advanced data analytics to this picture, not the least of which is the interacting feature tool. It's the only type of tool of its nature that we're aware of at Stantec, it can systematically compare and correlate all the features from any number of ILIs to identify overlap and proximity. It does that completely systematically, interacting every possible feature against the others, to come up with that very comprehensive list of interacting features. So I would say that the next element of technology that we're going to see that we haven't already seen yet is elements of machine learning. Machine learning isn't the answer to everything. It does have its purpose, and it also has its limitations. I expect that we're going to see machine learning in some cases of, for example, pulling out patterns in trends that are very challenging just due to the volume of data. It's very challenging for analysts to do. So the machine learning is going to help us cut through the volume of data that we're getting and narrow it down to a small subset so that subject matter people can make some final decisions.
Yeah, agreed, James. We are seeing advancements in AI and machine learning for ILI review, for underwater camera review. So the industry is definitely moving forward in that site and light. Jerry, we're kind of coming to the end of our Q&A period. Any thoughts on the wrap up?
Thanks, Dennis. If that's all of the questions we have, we can go ahead and end the recording. Thank you, everyone, for coming. We will be sending out a recording of the webinar to everyone who registered. So thank you very much for joining us today.
Thanks, everyone.